first one, maybe the most simple, is the file system check. So when we reboot after a crash, what we do is we just scan the entire file system and then determine from there where the corruption may be. So this appeared in sort of older file systems like FFS and ext2. And the good thing about schemes like this is during runtime, it's very fast because we don't have any overhead for consistency. But the problem is that when the system crashes and we need to scan the entire disk, even with extremely fast disks, this can be quite slow. So even with a modern disk, say we have like a 4 terabyte SSD or something, even if we are generous and say it has like 4 gigabyte a second read speeds, it could still take about 10, 15 minutes to scan the entire disk, which is not extremely long, but if we want some sort of high availability file system in a cluster or something like that, it's not quick enough. Another way we can guarantee consistency is through journaling. So we log metadata first to a separate area on disk called the log. And we can also log data, just either or. And after the write's complete, the data is then written to its original place. So journaling appears in most file systems now. At the time of this paper, I'm not sure ext4 was available, but ext4 has it too. And what's good about journaling is that it's very fast to recover the file system because we just need to read the log and see if anything in the log is broken. But the issue with journaling is that we need to order the journal rights of metadata. So while some metadata is being written first in order, we have to wait before we start the next write. And also data must be written twice, to the journal and then to the other area on disk, which is quite slow. Another technique is called soft updates, where we can track dependencies of metadata blocks in memory and then order these writes to disk so the metadata is always consistent. Now, soft updates quite fast, even though it introduces some ordering, but from reading the paper, it was extremely hard to implement. And this is a long time ago, and it didn't make the idea sort of didn't spread outside of BSD where it originated, I think, as of writing in this paper, which was 2012. So maybe it became popular after, but I'm not sure. And finally, we have copy on write, where instead of overwriting stuff in place, we just write data and metadata to new blocks every time. And after the write is done, then we add the information to the file system tree. The performance is good with copy on write, but it still introduces some sort of ordering, because when we're switching over to the old versus the new metadata view, that is the ordering point. And from this paper and other papers I've read too, copy on write seems to be now notoriously complex to implement and very hard. So a common issue with all of these methods, except the file system scan, is that they all introduce some sort of ordering into the writes. And as we talked about, ordering worsens performance because we need to wait for things to complete instead of using the disk. And it introduces complexity in the update path. And not so obvious, but at times ordering can require the cooperation of lower levels of the storage stack. So for example, we may need a proper disk flush command to implement ordering. So we need to flush this write before the next one starts. And if the disk doesn't have this command, or the command on the disk doesn't work properly, or like we assume it to, then the ordering won't work either. And there's nothing we can do about that. So in this paper, they introduced what they call no order file system, NoFS, which the claim is that it's a lightweight, consistent file system with no ordering. But at the same time, we make files immediately available upon mount. And the two major design points of the file system are something called backpointer-based consistency and the choice not to persist allocation structures like a data block bitmap or something like that. So if we just take an example crash scenario, we have file A, which has a block, but file A becomes truncated, and this data block is allocated to file B. And what happens is when we want to update these structures on disk, the data block and file B are updated on disk, but then we crash. And file A does not get updated on disk before the crash. So what happens is that now both files claim to own this data block. So this is a sort of example scenario we can look at, a very simple scenario to introduce what they call backpointer-based consistency. So if we think about the view of the file system in terms of logical identity, we can say that the logical identity of a data block is the file it belongs to, and the logical identity of a file is the list of directories it belongs to. So if we can embed this information in each block, we can then find the owner of the block through the backpointer. And then when we have disagreements about who owns a block, as in the previous example, we can just check the backpointer as the final source to make a decision. So in this diagram on the right, we have a data block on the right, which has a backpointer in it to the file it belongs to. And the file also has these forward pointers, as in regular file systems, to the data block. And the file can have one or more backpointers to the directories it belongs to. And then the directories will link to the file. So if we sort of revisit this scenario as before, we have this file A, but now instead of just having the forward pointers as usual, we have these back pointers. And we truncate A again, and the data block is allocated to B. Now, when the data block and file B are updated on disk, but we crash and file A is not updated on disk, so they both think they own the data block. When we read these blocks of the disk, what we can do is decide now what file is the data block pointing to using the back pointer. Excuse me. So when we read these blocks now, we can know who the original owner is. And backpointer-based consistency, these backpointers, it's a simple idea, but as they demonstrate in the work, it allows us to essentially recognize and fix pretty much most crash consistency problems. The second part of the design is that, so for allocation structures in the file system, we want to know where we can place new data on the disk. But what happens if we crash and the structures become inconsistent? Then we may think some block on the disk is free when it's not, and we can overwrite, some important data. So for example, we have file A in memory and a data block. And then we have these data block bitmaps on disk and in memory. And then we have this free block at the beginning of the bitmap. So we allocate this data block to file A, and then we write file A and the data block to disk, but we crash before we update the data block bitmap. So now if we were to read the bitmap from the disk, we would see that this block is free, which is incorrect, and we might override it. So we can recover these structures using the stuff we talked about before. We could scan the file system, or because if we use journaling, we could just recover the log. But the goal of this file system was to be fast and lightweight, which means we don't want to scan on the reboot because it's not good for availability. And we don't want to order allocation structure writes to disk like journaling, because it can be slow. So what they do in NoFS is they don't persist the allocation structures, they're just entirely in memory. So during the file system operation, we have a background scan, which builds the structures incrementally. So if we take, for example, ext2, at the beginning when we reboot, we would scan the file system, and we have files on the left here and data blocks on the right. And if a file points to the data block, we mark this block occupied in the data block bitmap. So while this is happening, we can't do anything. it's the scan at the beginning of the reboot. We can't use the file system while this is in place. But in NoFS, it's built incrementally while the file system, during operation of the file system. So they have a data block bitmap like before, but they also have this bitmap, which they call a validity bitmap, but I've just called it the scene bitmap in these slides. And because we're building up the block bitmap incrementally, everything will be marked free at the beginning. But as we know, everything might not be free. We just might not have seen the blocks yet. So we need another bitmap to verify whether this block has been seen yet before we reallocate it. So for example, we have file A here and we have a data block, and file A is pointing to this data block, and we read this data block, and we also recognize that it is pointing back to file A. So the back pointer points to file A, and we have an agreement about who owns this block. So we mark it as seen in the scene bitmap, and we mark it as occupied in the data block bitmap. We go to file B, and we see that when we've read this data block, we notice that the back pointer points to file B, but file B doesn't point to this one. So there's a disagreement on who owns the block, and we just mark it as free because it doesn't belong. And then we repeat the process for the rest of the blocks. So those are the two main points of the file system, but so we can see how it performs. In the paper, they do quite extensive reliability testing against ext2, but we're not going to show it in the presentation. We'll just look at the performance. So we want to see, in general, how fast is the file system, but also how much of an effect do the scans have on the performance of the system. So in these benchmarks, we compare to ext2 and ext3. And the reason we benchmark against ext2 is because, as we saw before, it doesn't have some sort of complex write ordering. It just scans the file system on a reboot, which means that in general, the normal operation of the file system is very fast. And then we compare to ext3 to compare against the file system that has journaling, so suffers from ordering penalties. And if we look at the graphs, in general, the NoFS, it's as fast as ext2 and in some cases faster than ext3. And when we see ext3's performance drop a lot, for example, in these metadata micro benchmarks, it's because the journaling overhead introduced just makes the performance worse, and the ordering overhead as such. But to compare NoFS and ext2, we don't have these ordering penalties or journaling penalties, so it's very fast compared to ext3. Again, they put the file systems through a number of macro benchmarks, but they don't really look much different than the micro benchmarks. So we have NoFS being as fast as ext2 again, and in some cases faster than ext3. So as we know, with NoFS, we want to have what we call high availability. So upon reboot, we want to be able to use the file system immediately, and we don't want to scan the whole file system like ext2. So we build the allocation structures incrementally, and this kind of a non-negligible effect on performance. So in the graph on the right here, we have the time on the bottom and the speed, the write bandwidth over time. And what they do is they start scans at 0, 60, 120, etc. And at the same time, they start some writes. But the two lines indicate that the writes either started at 0 seconds or started at 20 seconds. So when the writes started at 0 seconds, they end up, interleaving with the scans. But when the writes start at 20 seconds, there is no interleaving with the scan. So as we see on the graph, when we interleave the writes with the scans, we may not have a choice in that matter if we just start using the file system. And the write bandwidth is roughly halved, as we can expect, because the scan in the background needs to scan blocks to build up the allocation structures, which causes contention at the disk, and we can't use the whole bandwidth for the writes. Another thing we can look at is how much data can we scan, how quickly with the background scanners. So on the graph on the right here, we have the runtime and the time taken to scan the blocks. And it takes quite a while to scan a gigabyte of data in the file system, but this paper was a long time ago. It was in FAST 2012. So the disk they use in the evaluation, if I remember, it only had 70 megabyte read. So it can be slow to scan data blocks in the background, to build the bitmaps or whatever, but it could be better given modern disks, but still a non-negligible penalty here in terms of time for scanning. And one sort of thing about NoFS is that, because we need to verify blocks before they're used, and what can happen is that, let's say, for example, we want to run ls on a deep directory, and so this command here, ls-li, which contains calls through stat. So stat will see, for example, the size of a file. What will happen is that if the directories contain a lot of unverified blocks, suddenly when we call this ls, now we need to verify all the blocks in the directories. So we have this recursive ls call, and on the right we have a graph here where we have the time on the bottom, which is the time after reboot, and then on the left we have the time it takes for ls to complete. So we have 128, 256, and 512 megabyte of data in the directories. Excuse me, the time on the bottom is the time of the scan. So the scan finishes here at 250 seconds. So for example, when we run this ls command at 140 seconds and we have 128 megabyte of data in these directories, ls takes about 11 or 12 seconds to complete. And when we have 512 megabyte in the directories, ls takes over 40 seconds just to complete one ls command. So there's quite a serious performance penalty here, but it only applies to the first scan of these unverified blocks after a reboot of the file system. So the penalty is there, but perhaps it could be acceptable if it's just the beginning. Depends on the users. So to conclude, file systems in general can pay large performance and complexity penalties to implement consistency because of things like ordering, which can also require at times lower level hardware support too. So in this paper, they introduced this NoFS, which is a file system without ordering and no persistence of allocation structures, but at the same time, we can recover from a crash. We can sort of claim high availability because we can use the file system right away without a sort of long initial scan. And while the performance is high and it's crash consistent, even though the performance dips during scans, maybe it could be acceptable. As we saw in the graph, it only reduced write bandwidth by half while scans were active. And scans won't be active the whole time, they'll just be active for a period of time at the beginning after the reboot. So we could claim acceptable performance during the scans and extremely high performance during normal operation. That's it. Thank you.